So, dear colleagues, good morning, everybody. Thank you. I would like to actually present some old news. This is about a study that we did. It was published in 2016, but we didn't really have the possibility to propagate it a bit more. So, it's about, the idea is analyzing settlement dynamics, which is a fancy word to say how settlements or human settlement behavior changed over time. Actually, on last year's EAA, there were some during the discussions. There were some suggestion that we might want to try this, and I said, we have done this in 2016, but nobody knows. So I decided to do a bit of a PR. So first to say something about what I mean under archaeological theory, and why I think it's important when dealing with spatial data. Then I will talk about interpreting the evidence. So how do we get from archaeological evidence to actually talking about human activities in the past. Then I will try to briefly explain what the evidence density estimation function is, and then a practical example of it in implementation. So you might find something quite practical at the end of the presentation. So first, to the theory. This approach is based on the theory of community areas of Eugene Neustupny, which basically states that what we observe are so-called settlement area. It's archaeological components that we excavate, we register them, we describe them, and they contain all the artifacts, all the evidence, and they represent an imprint of past community areas that existed at this location. And there are, of course, there are some transformations and which we have to account for. So this is a basic statement, basic assumptions that individual finds are points of archaeological evidence, and they are a result of past human activity, and it's the optimistic belief that we can use them to study past human behavior. And that variations in spatial-temporal distribution of this evidence to some degree mirror changes of the actual settlement patterns. And we can infer on the settlement dynamics by studying this evidence and how it changes. So our original motivation actually was of course there has to be a scientific question, but often in archaeology you have data, and we had lots of data on settlement sites, which lied since at least the 90s or even earlier in digitized form in the archives, and it's over 130,000 records of archaeological actions with associated archaeological dating, localization. There is some indication of degree of accuracy. So we wanted to find out what to do with this data. Also, there is a growing number of radiocarbon databases, and we see efforts of summing radiocarbon data to produce temporal frequency distribution curves to infer on population or demography even. We don't speak in our so me and Dagmar Dresslerova about demography, because I think it's a very strong belief that we can. What we see is settlement densities, not people densities. Not yet. Okay, so this is just a screenshot of the article. You are welcome to look at it if you want closer details. So let's. I will try to explain the function, the method on an example. So let's say we have some sort of field survey, and evidence is found. So a fragment, or could be anything. So this fragment, of course, is recorded. So it gets spatial coordinates. It gets temporal coordinates, so it's dated. Doesn't matter if it's archaeological dating, like typo-chronology, or if it's scientific dating, radiocarbon-dated chronology. We have some temporal coordinates. Then what's important? We have some degree of spatial accuracy. Of course, it can be GPS coordinates, where this is almost irrelevant whether it's an area or a point. But with lots of databases have just location accuracy on the cadaster, so you have a very wide dispersion of the uncertainty. Next, there is the temporal accuracy. Of course, if it's archaeological dating, you have some uncertainty stemming from the length of the interval of the dating. Or if it's C14 dating, you have the standard deviation given by the laboratory that did the dating. And so this is just the archaeological evidence. But what's important to keep in mind, in accordance with the settlement area theory, that this find actually represents evidence of a settlement or an area of settlement activity that existed, and we don't know in which part of that area the find was located. So, and what we are interested in is the settlement area itself. So how to take that into account? So we know that this settlement had some radius. I'm just going to use the word settlement, not area of settlement activities. It's easier. So it has some radius. So it's an area in space, but also the settlement had some duration. We don't assume that the settlement lasted for 1 year, and that evidence can come from any time and any place in that settlement. So of course we don't know where the center lies. So the image might look like this, or it might look like this. There has to be some overlap, but it's two volumes in space and time that are somehow related. And the way to statistically assess this is to integrate over space and time. So the evidence estimation function calculates the probability that the side of activities producing the observed type of evidence was present at the specific coordinates in space and time, given the spatial-temporal coordinates and measurement uncertainties of observed evidence and an expected radius and duration of these sites. So, in simple words, it gives us a probabilistic map of settlement sites for any arbitrary time slice that we choose. This is quickly how the spatial. So it has two components. It has a spatial component and a temporal component, and so the spatial component, there is the part of the it's a function. This represents the probability distribution in space. So the center is given by the location of the find of the evidence. Then around it we have a region of uniform probability that's just given by the area of the radius of accuracy of the location, and then we have a region that's given by the size of the expected settlement. So we have to, let's say, by expert knowledge, determine or plug in some expected diameter or radius of the settlement. This is integrated. I'm not gonna go too deep into that since we don't have so much time. Okay, the temporal component. We have two types of evidence. We can have archaeologically dated settlement, where we are dealing with uniform probabilities. Again, this is for the registration of the find. This is the interval of the dating, and then we have some decreasing probabilities to account for the duration of the settlement. So the settlement would have begin here and ended here, but also anywhere on this scale or in that interval. For radiocarbon dating, it's similar, but here we are dealing with the actual probability distribution that's produced by the calibration of the radiocarbon data. So this is a way to combine the data to create to come to some probabilities that can be then further combined, and so the resulting spatial-temporal probability density is a result of multiplying the spatial and the temporal component, and then the probabilities stemming from the single points of evidence is combined using Hopper's rule for concurrent testimony. So this also eliminates the let's say the bias that or there would be a unnecessary intensification if we were to just sum the evidence. Then we would have, if we have some area with lot which was very well explored, we would have peaks in apparent density, but that would be a bias. So okay, the result, if we apply this function to our data set, this is just so date points in space which are dated and assign either archaeological or scientific dating. We can interpolate them in space and time, and we can produce time slices like this, where all these biases that I mentioned are already taken into account, and we get probability maps which we can then use to further work with the evidence in a correct way. So we can do environmental studies. We can look at site densities. So we can look at how the population dynamics changed. And you see there is this is just an example region, but you see sometimes in some time slices there is shifts. So we see something like how the population or how the site density moves in space. So just to sum up, why is this method better than just using distribution maps or C14 summations? It takes spatial and temporal uncertainty into account. It models settlements at volumes in time and space, so it's according with archaeological theory. It needs no spatial or temporal binning of the input data. It allows for combined use of archaeologically and radiocarbon-dated evidence, so we get much more evidence to work with, and produces easy-to-use probabilistic maps and can be summed to analyze fluctuations in settlement density over time. So this is just a glimpse for Bohemia. We applied this for the whole archaeological map of the Czech Republic, and we were able to study how the settlement density changed over time in different regions, and there turned out to be quite interesting regional variations. So to conclude, or at the end, I promised something practical. I created a QGIS plugin, which is relatively easy to use. You can find it on using QGIS. So first, of course, you need your data. You need your spatial data prepared as a point file. It has to indicate the accuracy in meters, the mean of the dating, the Earth's uncertainty, and the dating type. So it's either uniform probability distribution for archaeological dating or normal probability distribution NPV for C14 dating. Then you just install this plugin by searching for EDE interpolation, and you just select which fields to use, model parameters, so expected settlement duration, settlement diameter, output parameters, what time steps you want the slice to create in. You can put some restraints on it and pretty colors. And also you can specify a CSV file where the summation of the results will be stored. So produces time slices like this, adds them to the map as raster layers. You can just switch between them. It also produces GeoTIFF time slices. So these are in floating point accuracy, and you can use them for further analysis. And also it produces a rendered version which can be used to produce these nice animations. And lastly, there is the summation in the CSV file. So you have the date, BP, BC, sound value for it's in the highest possible temporal resolution that the radiocarbon calibration curve permits. And this could be then used, for example, as a proxy for exploring fluctuations in settlement density. So thank you for your attention. Here are some links if you want to